In this lecture, we will discuss the first. We will discuss zeroth law of thermodynamics. Zeroth law of thermodynamics. Suppose you have three bodies. This is body A. Suppose this is body B, and this is body C. A, B, and C. So first we imagine that this body A is in equilibrium with C. Suppose this is in equilibrium with this one. And this body B is also in equilibrium with the C. From this we can say simply that the body A and B are in, can say, thermal equilibrium. So we can write the statement simply: if body A is in thermal equilibrium with body C and body B is also in thermal equilibrium with body C, then we can say then the bodies A and B are in thermal equilibrium with each other. Equilibrium with each other. So we can take a simple example of, suppose, thermometer. Which is simply based on this law. Okay, that means this thermometer is basically based on the zeroth law of thermodynamics. Okay, now we will see the first law of thermodynamics, and we will try to derive some of the equations related to this law. Okay, so first law of thermodynamics. It is basically it is the law of conservation of energy and can be stated in following ways. Okay, that means this law can be stated in various ways. First one, we will take the statement that the total mass and energy, very important, mass and energy of an isolated system remains constant, you can say, remains constant or conserved, you can say. The second statement we can write here: energy can be transformed from one form to another form, but energy can neither be created or destroyed. Nor destroyed. Okay, this is one more statement. It is basically it is impossible to construct a perpetual motion machine which could produce work without the expenditure of energy, without consuming any energy. That means this perpetual motion machine would be one which can not consume any type of energy but can produce work, but that is impossible. So it is one of the statements of first law also. Now coming to its mathematical equation. So mathematically we can write internal energy is written by capital U. So we will write small change in internal energy, that means du, on or infinitesimal change in this internal energy is basically equal to dq, small amount of heat plus small amount of work done, dw. Okay, suppose we have two states of a system. Suppose this is state A and it changes into, suppose, state B. Now to find this change in internal energy from state A to state B, what we will do, we will simply integrate this one. That means if this is equation number 1, we can simply write it as the du state is changing from A to initial to final is B. Okay, and similarly for other two terms we can write integral dq A to B plus integral A to B dw. Okay, if you have this type of integral, that integral and differential of some function, this differential and integral will go, it will be simply equal to x. Remember this. So as per this it will be simply equal to u. Okay, so I can write this u, but I have lower limit a, upper limit b, and this will be simply equal to, I can simply write it as equal to q from A to B. Suppose total is equivalent to amount of heat q, and suppose this is total work done will be, suppose, w. Okay, or I can write this as, suppose this is final ub minus ua is equal to q plus w, or I can simply write it this form, that change in internal energy from going to the state A to state B will be equal to q plus w. So this is the equation you have to remember, that change in internal. But here this q as well as this w, they both depend upon the path followed. That means q as well as w, both are path functions. But if we make an algebraic sum, but this change in internal energy, this is a state function. State function. That means it depends upon the initial and the final state only, and not upon the path followed. So if I take individually q, this is a path function, individually w, this is also a path function, but their algebraic sum. Always remember that q plus w will also be then a state function. Why? Because this is simply equal to the change in internal energy. But if you take only Q or W, those will be the path functions. Okay, so this was little about the equation of first law of thermodynamics. What you have to remember, change in internal energy is equal to Q plus W. Okay, now we will take different cases here. Suppose at constant volume, we know if V is equal to constant, then change in volume will obviously, or dV will be equal to 0. Okay, but we know also that the work, if this is an uh, simple work, that means volume expansion type of work, then we can write this equation in this form. That means this W will be simply equal to minus P external, you know this equation, dV. Okay, so as per this case, if dV is equal to 0, if this term is equal to 0, then 0 multiplied by this one will be obviously equal to 0. That means W will be equal to 0. So if I write, then the change in internal energy is equal to Q plus W. But as per this case, W is equal to 0. So I can simply write as W is equal to 0. So change in internal energy will be simply equal to Q, but I will put a simple subscript that at constant volume. What is the condition? At constant volume, the change in internal energy is equivalent to the heat supply or absorbed. So you can write this mathematical equation in this term also, that heat absorbed at constant volume increases the internal energy. Okay, so now we can take one more case. Suppose case second, if it is a case 1, suppose at constant temperature. These are very important equations you have to remember. Then in the videos, upcoming videos, wherever it is written as QV, you should be able to remember this equation, that QV is also equal to delta U, or delta U is equal to QV. How? This is we have already done. So at constant temperature, we have this equation at the beginning of this chapter, or in the lecture 1, we already discussed that this change in internal energy is equal to NCV delta T. Okay, so if this delta T is equal to 0, So this term will be equal to 0. So from this equation what we got, that at constant temperature change in internal energy will be 0. So if we use the equation that we know change in internal energy is equal to Q plus W, this much is equal to 0, 0 will be equal to Q plus W, or you can simply write it as Q is equal to minus W. Very simple. So this equation basically tells us the amount of heat absorbed. Suppose if this Q is basically the amount of heat absorbed by the system, or in place of system you can take gas system from the surroundings is equal to the work done. Here you have to see this negative sign, it is negative. What does it tell? That this is equal to the work done, but by the system. Very important. Work done by the system on the surroundings. So this is the sign convention also. So this will be the case at constant temperature. One more point you have to remember regarding for a cyclic process. For example, we will take a cyclic process. For cyclic process, this change in internal energy is always equal to 0. Change in internal energy is always equal to 0. So what does this mean? That means Q plus W will also be equal to 0. Cyclic process, what does this mean? That means if suppose state A changes to B, B changes to C, C changes to suppose D, D changes to suppose E, and finally this E changes to back to A. Suppose if this was having internal energy some U, U minus U will be simply equal to 0 or some value, because it is the it will come back to the initial state. So the change in internal energy will be simply equal to 0 for a cyclic process. Okay. Now one more case is at constant pressure. I am just revising these things. Basically you should have gone through these terms in the previous classes, but try to remember these and also go through some textbooks to find various answers regarding these equations. Okay, so at constant pressure, that means I am now supplying heat at constant pressure. Always remember this will be equal to enthalpy. Enthalpy is written as H, so it will be enthalpy. Okay, So therefore first law becomes, that means we have first law delta U, that means change in internal energy, change in internal energy is equal to Q plus W. Okay, if this is heat supplied or absorbed at constant pressure, then you know this QP can be replaced simply by the H. So what you can write, you can simply write change in internal energy is equal to H plus W as well. Okay, it's very simple, this one. Now one more type of process we have for adiabatic process. For adiabatic process, that means Q is constant, dQ will be obviously 0, or uh, if we take, that means total Q will be equal to 0. So we can write simply the change in internal energy is equal to 0 plus W, or can simply write change in internal energy will be equal to the work done. If suppose this work done is the pressure volume work of a gas, so we can simply write it as minus P external, pressure is constant, delta V. You have already derived this equation in terms of work done. So this work is, this W is basically equal to the loss in internal energy. Okay, now we will see one more concept here, enthalpy, or this is also called as heat content. It is simply represented by capital H. The short definition what you have to remember regarding this enthalpy or heat content, how you can define this, simply the thermal changes occurring at constant pressure. Okay, that means this enthalpy is basically equal to U plus PV, or you can write this as the small change in enthalpy Th will be equal to du. That means this is function 1, this will be the function 2. From the differential equations, what we do there, we basically do differentiation this way. We hold the first function, differentiate the second, plus hold the second, differentiate the first. Okay, so this is very simple. Suppose this is now equation 1, this is equation 2nd. And what you have to remember regarding this h, this is a state function. That means it depends upon the initial and the final state only. And also this th is an exact differential. That means it will be exactly differentiated. Okay, exact differential. Okay, now from equation 1, that means this equation, but we have, if we have suppose two status, so for two status, suppose if one state is written as h1, suppose we can write for two status h1 is equal to u1 plus p1 v1, and for the second we can write h2 is equal to u2 plus p2 v2. Okay, very simple. Now what we will do, we will simply take the difference. That means we will write change in enthalpy delta H will be simply equal to H2 minus H1. Okay, but this H1 is equal to this much, and this H2 is equal to this much. We will simply substitute the values here. So in place of H2 we will simply write U2 plus P2 V2, negative is here. Then in place of H1 we will write U1 plus P1 V1. Okay, now simple can simplify this. U2 plus P2 V2, you can take this negative and multiply it here. It will be negative of U1 negative of P1 V1. So we can simply write it as, that means we can take similar terms U2 minus U1, and if we take negative common for these two terms P1 V1 and P2 V2, we can write negative term here. So we can write then P2 V2 minus P1 V1. Okay, so the delta H will be simply equal to, this will be simply equal to delta U, change in internal energy, plus, suppose if this P1 is equal to P2 is equal to P, that means at constant pressure, you can say. So in we can take this P outside, we can simply write plus P into V2 minus V1. Okay, so it will be plus here, sorry. This will be plus here. So you can simply write then delta U plus P delta V also. So delta H is equal to this much, or you can write delta H is equal to delta U. If this is the pressure volume work, you can write as plus W as well. Okay, then from first law, if now work is done by the gas, then in that case we can write delta U, basically delta U is equal to, we know is equal to Q plus W. If we take the minus W here, that means this W will be minus W is work done by the gas or by the system, you can say. So negative. Suppose if this is equation number 3, this is 4. Okay, so what we can write, equation 4, this one then becomes, that means in place of delta U we can insert Q minus W value. That means we can write delta H is equal to Q minus W, and then it is plus W. So simply this minus and plus will go, so we have delta H is equal to QP. So this is the statement that heat absorbed at constant pressure is basically equal to the change in enthalpy, or simply equal to the enthalpy, total enthalpy. Now you have to remember, if this delta H is positive for a reaction or for a process, then process will be endothermic. Endothermic, that means that process will absorb the heat. Okay, if delta H is negative, that means the process will be simply exothermic. Very simple, you know these things from the previous knowledge, but I am just revising here. Now one more thing is that a relation between delta H and delta U. Now from first law of thermodynamics, what we know, delta U is equal to Q minus W. Okay. We can also write it as, if this is W is the pressure volume work, we can write as Q minus P external del V. Okay. Now at constant volume, you know simply delta V is equal to 0, so delta U is equal to Q. Again, we know that this delta H is equal to QP. We have derived this in the above equation. So what we can write then, we can simply, we know this from above equation 3, or I will write it one more time here, that equation 3 is basically delta H is equal to delta U plus P delta V. Okay, so let also N1 moles of gaseous reactant changes into N2 moles of gaseous product. Okay, but the condition is that are under constant temperature and pressure. So then in that case we have the P pressure is constant, P1, otherwise we would have written as P1 V1. Pressure is constant, we will simply write P. PV1 will be equal to ideal gas equation N1. Suppose N1 moles, R is constant, temperature is also constant, we will write it as nRT. Or we can write PV2 is equal to N2 RT. Okay. Therefore, if we take the difference of these two, that means PV2 minus PV1, it will be simply equal to N2RT minus N1RT. So what you will write, P delta V is basically equal to, this is N2 minus N1, that means it will be the change in number of moles. You can write it as N but gaseous. Okay, delta Ng RT. What is delta Ng here? Moles of gaseous product minus moles of gaseous reactant. That means, therefore, we can simply write that delta H is basically equal to change in internal energy delta U plus, in place of P delta V, what we will write, delta Ng, that is change in the number of gaseous products, R into T. Okay, so these things you have to remember. Okay, okay, this one also. In the next video, we will take the applications of first law of thermodynamics. Please go through these equations very carefully. These will help you in solving various MCQs particularly asked in CSIR net. Okay, thank you.